Now we will look at various types of energy that I just discussed. What are they, and some basic idea about them before we go along. So one of the major types of energy is electromagnetic radiation. Sunlight is a form of electromagnetic radiation. So is X-rays, radio waves, infrared, microwaves, ultraviolet, etc. And this electromagnetic radiation can be thought of oscillations in an electromagnetic field. Propagating oscillation in an electromagnetic field is defined as electromagnetic radiation. And a small section of this oscillating field is visible to us. So visible light is a form of electromagnetic radiation as well. So since electromagnetic radiation is a wave, we can think of waves having wavelengths and frequencies. Correct? So wavelength is basically the distance between one peak or one trough to another peak and another trough. Okay, the distance between two peaks, two troughs, or two equally repeatable segments along the propagation of the wave. Okay. So that's wavelength. And frequency is the number of waves that are being transmitted through a certain location within 1 second. Okay, so number of waves per second, so it's second inverse, and the unit is hertz or second inverse. Okay. Now electromagnetic waves the wavelength or the frequency can vary over a very large range. Okay. So you can have wavelengths that are extremely large. So you can have wavelengths of the order of kilometers, 10 to the power 3 meters, or 1000 kilometers, 10 to the power 6 meters. Okay. Typically, radio waves, AM, FM, and TV waves, that is satellite television, the kind of wavelengths these emit, and the radio waves that are emitted, that are being captured by your radios, these are of this order. So 10 to the power 6, 10 to the power 3 meters, the wavelengths, and clearly these waves have much lower frequencies. Okay. So their frequencies in hertz is also between 10 to the power 3 to 10 to the power 6 hertz. So remember, wavelength and frequency are inversely related. As the wavelengths increase, the frequencies decrease, and vice versa. Okay. Then you have the microwaves on your standard microwave oven that you often find as an electrical appliance. So their frequencies range between 10 to the power 9 hertz to 10 to the power 12 hertz. So 10 to the power 9 to 10 to the power 12 waves propagate through a certain region per second. Okay. And their wavelengths are between 1 meter to 10 to the power minus 3 meters. So 1 meter to 1 millimeter. That's their wavelength range. Then you go to the infrared region of electromagnetic radiation, which exists between 10 to the power minus 3 to 10 to the power minus 6 meters. So 1 millimeter to 1 micrometer. Okay. That's the wavelength range, and the frequency range is 10 to the power 12 to around 10 to the power 14. So this is the thermal infrared radiation as part of your electromagnetic wave. Then you get your visible range, which is between 0.7 to 0.4 micrometers, their infrared range, and typically close to 10 to the power 15 hertz. Okay, in terms of the frequencies. This narrow visible spectrum is the where you can see all your visible light, the red light, the blue light, the yellow light that you can see in your in the visible range. Beyond the visible range, at even lower wavelengths, you have ultraviolet radiation, the UV radiation that is harmful to the skins and causes skin cancer. So just beyond that, even shorter wavelengths, you have UV radiation. Then you get to even shorter wavelengths and even higher frequencies, like X-rays that is used in medical diagnostics, and gamma rays, which is extremely energetic forms of electromagnetic waves that are extremely harmful and carcinogenic to humans. Okay. So all of these types of waves are basically different aspects of your electromagnetic spectrum. Here we are seeing your light, visible light, and here you are seeing your typical hand in the infrared region, where because of the temperature of your hand, you are getting infrared radiation of various intensities. Higher intensities or hotter regions are showing up as red, while your fingertips are colder and hence they are showing up as green. We will discuss this point that hotter substrates emit radiations at higher intensities and lower wavelengths typically than colder substrates, and we will see this point later. To the right, we have the solar radiation spectrum, which is basically the electromagnetic spectrum of solar radiation which hits Earth. Okay. The top line, the black line, is the solar radiation spectrum as it hits the top of Earth's atmosphere, and this red segment is the solar radiation, that part of the solar radiation that is transmitted through the atmosphere and hits the ground. Okay, because part of the solar radiation gets absorbed by the atmosphere or reflected by clouds and dust and other aspects of the atmosphere back to space, so that part does not reach the atmosphere, but the rest which does reach is given by this red region, and which is hitting the top of the atmosphere is given by the yellow region. And here we are seeing at the x-axis the wavelength of this spectrum. It starts from around 250 nanometers, so 215 to 10 to the power minus 9. So if you see here, it's around this region, in the beyond the ultraviolet region. It starts there and goes all the way to 2500 nanometers or 2.5 micrometers. So just beyond 10 to the power minus 6. So it goes into the infrared region here. And you can see the visible spectrum, which is extending from around 400 nanometer region to around 750 nanometer region. So this is the visible part of the radiation that you can see with your naked eye. Okay. So this region, higher wavelengths is the red light, and less than 500 is the blue light, and in between is the green, yellow, etc. Okay. And you can see the solar spectrum kind of has different intensities, that is how much of the sunlight is within a specific wavelength you can see. And the most intense part of the solar spectrum is in the visible range. So a significant part and the peak of solar radiation is where we can see the sunlight. Okay. But also a significant part is in the ultraviolet range and in infrared range beyond this. Okay. Another important aspect to note is that the energy that is contained in electromagnetic radiation is discretized, as Einstein discovered in one of his first seminal papers, by which Einstein and Planck discovered this aspect. That energy comes in discrete packets, which we call photons, and this is proportional to the frequency nu. This frequency here multiplied by a proportionality factor, the Planck constant, which is 6.626 into the power minus 34 joule seconds. Okay. So as the frequency of your electromagnetic radiation increases, the energy content of these discrete packets or photons is also increasing. So high frequency radiation typically have high energy photons, while low frequency, large wavelength radiations typically contain less energetic photons. Okay. So that's electromagnetic radiation. We will come to further discussions of EM radiation when we are discussing the solar cell technology, where we are harvesting sunlight directly to produce electricity. Then another type of very common energy is chemical energy. That is energy that is contained in the bonds of individual molecules. Okay. So this is the attractive bonds that are created between different atoms. So for example, oxygen molecule contains 2 atoms of oxygen held by attractive forces, the covalent bonds created by the electron clouds that are surrounding the oxygen nucleus. So it's kind of a also a potential energy, a chemical potential energy, and is also a form of electrical potential energy, because these are basically electrons which are bound. So this is basically a configuration within an electrical field, correct? We call them chemical energy or chemical potential because these breaking and unbreaking of these bonds are associated with the generation of chemical energy. Chemistry is associated with the breaking and unbreaking of these molecular bonds, so we call them chemical energy. So a common way to convert chemical energy, that is chemical potential energy contained in the molecular bonds, is through combustion, where you are using a fuel like methane reacting with oxygen and producing more stable molecules like CO2 and water vapor. In this case, the chemical energy that is being released by the formation of these new bonds, CO2 and water vapor, is much larger than the chemical energy that is consumed by the breaking of the bonds present in methane and oxygen, and hence the difference in the chemical energy between release and absorption is coming out as heat energy or kinetic energy of molecules that we see in typical combustion devices as an increase in temperature, like in flames. So we see a typical gas stove where your methane or LPG, whatever you are using, is being burnt. This releases a lot of thermal energy that you can use to cook your food or use to heat your house. Okay. And this is kind of the bond, that is the energy difference, as a one bond is broken and another bond is produced. And as we know, this is the fundamental form of energy that is being used in today's world to power most of our energy systems. The combustion process of fuels like oil, petroleum, natural gas, etc. So the chemical to heat energy conversion is a very important aspect of current energy technologies. Another form of energy is the nuclear energy, which we alluded to just in the beginning. That is the energy, the potential energy associated with the configuration of the protons and neutrons within the strong nuclear force field within the nucleus of an atom. And usually this is extremely stable, so nuclear energy is much harder to harness than chemical energy. But for certain atoms like uranium, the nucleus is inherently unstable. So these are extremely heavy atoms, which means it has a lot of neutrons and protons, and it makes it fundamentally unstable. So if a high energy neutron hits it, this nucleus can break into smaller nucleus of different elements, which we are calling daughter nuclei, and this breaking process basically generates energy. So because the daughter nuclei are far more stable than the parent uranium nuclei, and hence the extra energy that is being produced is generated, and this generates heat as well as extra neutrons that can hit other uranium nucleons, and hence create a chain reaction where one nucleus is hit by one neutron. It produces 3 neutrons, which hits 3 more nuclei of uranium. Each of these nuclei break out, generate heat, and also produce 3 more neutrons, which and hence the next side is 9 nuclei are hit, and so on and so forth, and a chain reaction happens, and a rapid rise in energy generation occurs. And this process is called nuclear fission. So fission basically means breakage, and this energy is being generated by the breakage of nuclei of heavy elements like uranium, like thorium, etc. And hence it's called nuclear fission. So all modern nuclear reactors are based on this nuclear fission technology. Okay. Nuclear fusion is the dominant mode of energy generation in the universe. So all the stars at their cores are basically generating or converting energy from the potential energy of nuclei into heat and light through the process of nuclear fusion. So this is the other end of the spectrum. Extremely light nuclei like helium, tritium, deuterium, which are basically isotopes of hydrogen, are less stable than somewhat heavier nucleus like helium, like lithium, or somewhat higher nitrogen elements like carbon. Okay. So at extremely high pressures, two nucleus of tritium and deuterium can come together to produce a more stable helium nucleus and generates energy as well as one extra neutron. So here also energy generation is happening, but energy generation is happening because lighter nucleus of lighter elements are coming together, fusing and producing nucleus of a heavier element which is more stable. Okay. And this process is happening in the core of the sun or in any other of the stars that exist in the universe, and that is the source of their energy. So all your sunlight, all the solar heat that comes to you is fundamentally produced through nuclear fusion. So nuclear fusion is the primary energy source of the universe. However, nuclear fusion is very hard to achieve because of the extremely high temperatures. You need millions of kelvins and extremely high pressures at which this transformation process can happen. Okay. So we have many region R&D centers in the world are currently aggressively pursuing nuclear fusion through tokamaks and other types of laser-based nuclear fusion technologies. And some success has been achieved. So it is hoped that in the next 30-40 years, we will reach a stage where commercial nuclear fusion power plants can become a reality. So just recently, like 4 or 5 months ago, they have been able to have nuclear fusion where they have been able to generate more energy than they are injecting into the system, which is an extremely important, though very preliminary step in the process. Finally, we also discuss mechanical energy. These are like very common forms of energy. For example, the kinetic energy of water. As water flows, the motion of water produces kinetic energy, which you can harness in a typical water wheel, medieval water wheel, or in a modern hydroelectric power system. The motion of water is converted to rotational motion of your blades, of your turbines, which generates electricity or which can pump water, whatever you want you to do. Similarly, wind motion has kinetic energy associated with it, kinetic energy of wind, which you can harness through windmills or wind turbines. Similar process. Another form of mechanical energy is kind of the potential energy of springs. So a spring mass system, when the spring is compressed, the energy is transformed into potential energy of the spring, which you can use to do useful work as well. So these are called mechanical forms of energy. Then we discuss thermal energy or heat energy, which is a very important type of energy. As we discussed, many of the fossil fuel systems basically are converting chemical energy to heat energy. Similarly, the nuclear reactors are also converting nuclear energy to heat energy, which this heat energy is then converted into electric energy through the power plant system, the heat engines basically of thermodynamics. So what is heat energy? Okay. Heat energy is nothing but a macroscopic form of molecular kinetic energy. The kinetic energy associated with molecules. So molecules of gases or liquids or even solids will have many types of motions. A gas molecule will have translational motion where the molecules will move with respect to each other. Solid molecules will not have that translational motion, of course, but they can have vibrational motion. Gas molecules will also have rotational motion. So if you have a O molecule, it can rotate around its axis. So all of these motions of molecules, translational motion, rotational motion, vibrational motion, and even electron translational motion. These are forms of molecular kinetic energy which we observe in the macroscopic world as heat energy. So, more energetic the molecular motions are, the more hot the substance appears to be. Okay. So, larger the molecular, the more frenetically the molecules are moving around, bouncing around, vibrating within a system of gas, liquid, or solid, greater is the amount of thermal energy content of that substance. And this heat is transferred through what are called temperature gradients. Okay. So there are temperature differences between 2 points, and thermal energy gets transferred from the high temperature source to the low temperature source, and this transfer is the transfer of thermal energy or heat energy. Now the SI unit of temperature is kelvins. So 0 degree centigrade is around 273 kelvins, 100 degree centigrade is 373 kelvins. So 1 degree centigrade is equivalent to 1 kelvin. Okay, but the origin is shifted to 273.15 kelvin for 0 degree centigrade. And change in temperature is associated with change in the heat energy of a system or thermal energy of a system, and this we can measure. So the change in thermal energy due to a certain change in temperature, delta T, okay, usually in kelvins, but you can also do it in centigrades here, is equals to the mass of the system into what is called the specific heat of the system, C, into the total change in temperature of the system. And specific heat C, whose units is joules per kg per Kelvin, is the thermal energy required to increase the temperature of 1 kg of a substance by 1 degree Kelvin. So when delta T is 1 and M is 1, delta E is equal to C. So that is what the definition of C is. So once you know the specific heat, you know the mass, and you know the change in temperature, you can find the change in thermal energy of your system. Finally, we also have electrical energy. So electricity has now become a very important part of our day-to-day technologies. It is the mechanical motion of your turbine systems is transferred into rotational motion of your generator shaft, which runs within a set of magnets, which creates the fluctuating electrical current, the AC current that we see in the grids today. Okay. If we define electrical power is the rate of energy generated due to flow of current, charged particles, usually electrons, etc., across an electric potential gradient. Okay. So primarily it's power equal to voltage into amperes, volts into amperes. So what is joules per second? So if one unit of electrical charge moves through 1 unit of electrical potential, volts, then it becomes power, watts, joules per second. Okay. So volt is the electrical potential, or current is the flow of charge in coulombs per second. So that gives you the electrical power generated by this electrical flow. And here we see the typical electrical grid in today's world. We have the electric generating station, where your generator, which is basically a rotating coiled copper wire rotating within a set of magnets generating electricity, going through high tension overhead transmission lines where the electrical potential is 230,000 volts, going to receiving stations, going to sub-transmission lines where the electrical potential is decreased to 69,000 volts, going to a distribution station, and then through distribution lines which are even lower electrical potential, 12,000 volts, and finally it goes to either industrial customers or residential customers through local transformer systems. So we will stop here today. We will continue in the next class. This is enough for one class, I believe. And we will continue with how to measure various units of energy and look at the role of energy in today's society. So thank you for watching this introductory lecture. Hope you enjoyed it and hope to see you again in the next.